Good afternoon, and welcome to the 37th Omega Row Distinguished Lecture. My name is John Fowler, and I'm the current president of Omega Row. Omega Row is the International Honor Society for Operations Research, Management Sciences, and related areas. Today, I'm honored to present the Omega Row Distinguished Lecturer, Professor Barry Nelson. Barry is the Walter P. Murphy Professor and Chair at the Department of Industrial Engineering and Management Sciences at Northwestern University. He's a leading researcher in the field of discrete event simulation with over 75 archival journal papers and 2 textbooks. In recognition of his distinguished service over the years in his career, Professor Nelson has received numerous awards, including the Informs Fellow Award, the Institute of Industrial Engineers Fellow Award, the Informs College on Simulation Distinguished Service Award, and numerous Best Paper and teaching awards. Following today's talk, Barry Nelson will be inducted as the 45th honorary member of Omega Row. On behalf of Omega Row, please welcome to the stage the 2011 Distinguished Lecturer, Professor Barry Nelson.
Thanks, John. I really appreciate being invited. When you look at the list of people who've been the Omega Row Distinguished Lecturer, it's really an outstanding group to get a chance to join. The 12th Omega Row Distinguished Lecturer was the late Dr. Alan Pritzker, and he was the person from whom I first learned computer simulation, and so I'd like to dedicate the talk today to him. So how does somebody like me end up in a career in simulation? Well, I was thinking back on the formative events in my simulation career, and the first time I ever saw anything that anybody called simulation was in a computer methods class as an undergraduate, where we simulated a dog chasing a runner and looked at evasive strategies. As a member of the track and cross country team at my university, I immediately knew simulation was valuable and useful. Shortly after I had the course from Alan in graduate school, I worked on a project for the U.S. Air Force, HEART project, which was designed, or the idea of the project was to try to reduce the risk of cardiovascular incidents among Air Force pilots, and my job was to design the risk reduction facilities. So that was my first taste of a real system with real data and real decisions, and my first chance to make real mistakes, which I certainly did. And then shortly after that, I was able to purchase my first, what you might call personal computer, a Commodore VIC-20, and in between playing Centipede, the first thing I did was code up a simulation of an MM1Q, and the graphics were about that good. And one of the things that I learned about simulation was it was really good for building intuition, because I knew a lot of mathematics about queuing, but I would never have recognized what one of those things looked like if I hadn't simulated it. So I'm a true believer in simulation, and right now is a great time to be a true believer. Simulation has never been more widely accepted. The software that we have for building models is absolutely spectacular. I believe that Inform's emphasis on analytics is actually going to increase the use of computer simulation, but change it from being a design tool, which has been the typical use, and more towards a decision support tool. Simulation is already being integrated in with other applications, and I don't think it's too far-fetched to think about simulations building themselves from the data and information that's in an enterprise management database system. So it's a great time to be doing simulation, but I also worry. Now, partly it's my nature, I'm just a worrier, but I know that there are ways that good simulations can go bad. Now, when I say good simulations, I mean correctly built, valid models that are appropriate for the situation for which they were designed, and yet still somehow we don't get everything that we should get out of that simulation. And so those are the things I'm going to talk about today. Simulation is risky business, the ghost of R.A. Fisher, simulators don't clean up their messes, and finally, the big confession, everything I told you is wrong. Not today, but up until today. Now, this talk was designed for a wide audience. Students, simulation novices, simulation experts, unbelievers in simulation, that's fine as well, and for researchers not who do research in simulation, but who might use simulation in their research. The only group that it's not designed for are my friends, right? My simulation pals. I saw Shane over there, and Michael, you can go get coffee. This talk is not for you. Because the research, of course, tends to emphasize things that are different or exceptional. And what I'm really going to talk about today are things that are very, very common. It's also the case that I'm not going to plug anybody's software. Now, simulation is very intertwined with software. It's very important for what we do. I do want to show you some little demonstrations, but they'll all be things that I coded up in VBA just to make my point. Nobody will be able to accuse me of taking sides on the software. A little more firm. So the first thing I want to talk about is simulation as risky business, and I'm also going to use this as a way to tell you about simulation if you don't know what I mean by stochastic computer simulation. So this will be the longest of the four, be a little bit of an example here, and you'll see a simulation just to know what I mean. But I also want to talk about this point about simulation and risk. This particular example was stolen with great thanks from a book called Calculated Bets by Stephen Skeena. I highly recommend this book if you want to see the application of simulation and operations research in managing and evaluating risk. So Highlight is a game. These days in the US it's only played in Florida, on which there's parimutuel betting, right? Which means you bet against the other people that are there and not against the house. They take their little take right off the top. And so it's played by 8 players. You're going to bet on one of those players to win. And the first player to 7 points wins. All right, so think of the players as standing in a line. The first 2 players come out. They play 1 point. Whoever wins stays on the court, and whoever loses goes to the back of the line. And the next player comes out. They play to a point. Winner stays. Loser goes to the back of the line. First 1 to 7 points wins. Now, it doesn't take any analysis at all to see that if it worked exactly the way I said it, you would be in a tremendous disadvantage if you were players 7 and 8 at the end, because lots of points could be won before you ever got out there. And so in Highlight, what's called the spectacular 7 scoring system evens up the odds by saying it's 1 point per win for the first 7 points and 2 points per win after that. And that makes it all even, right? Well, I don't know. Maybe that's not so clear, right? So does the spectacular 7 scoring system actually work? All right, so does starting position matter? How would a computer simulation person go about answering that question? Well, what we do is take players out of the mix. So the first thing we do is we assume that all players are equally good. So whoever wins is like a coin flip, probability of half. Then we write an algorithm in a computer language that implements the rules of Highlight. Hey, the rules of Highlight are simple. They were all in the previous slide. Not too hard to write a computer algorithm that does that. But of course, we get tired of flipping coins really quickly, so we'll let pseudo-random numbers stand in for the coin flips. And then we can do the obvious thing, which is run the algorithm for many, many matches of Highlight and look to see something about the percentage of wins by starting position. So let's run this little simulation. So give me a minute, JD, before we start this. So you're going to see a little simulation here in a minute. Along the top is the players, numbered 1 through 8. We're going to play a large number of Highlight matches, and it will display the percentage of wins by position. Since this is going to be an estimate of the probability of winning by position, it's going to have error. And that's one thing about computer simulations. Stochastic simulations, we estimate things, and so there's statistical error. So the third line down will show you the error in the form of a confidence interval, plus or minus, right? And that will update as we go along. And at the end, we'll see some results. So for example, this was the result of one simulation, player number 4 won, but of course we know that's not going to happen every time. Okay, let's go ahead and run it. Now, I didn't want to try your patience too much, so we'll run 5,000 Highlight matches. Certainly more than a person could actually attend in a year, but it wouldn't be hard to run 50,000 or 500,000 as well. All right, so you can see the percentages changing along the way. You can see the error in our estimates dropping as we go along, and we're creeping up on 5,000. And there we go. Now we've estimated those percentages to within about plus or minus a percent, so there's still some error left, but it's clear that the Spectacular 7 scoring system doesn't do its job. Player 1 and Player 2 have a significant advantage, particularly over Player 7. This is an example of what computer simulation does. It is, in a sense, we mimic the real situation, letting random numbers stand in for the uncertainty that's there, and we end up having to estimate whatever it is that we're interested in. Now, this was a really useful simulation in the sense of telling you a lot about how highlight would work, but even though we estimated those probabilities very precisely, I would bet that there's nobody in this room that would be willing to put their entire retirement savings or their entire next paycheck or next semester's tuition on one bet of highlight. Right? Because even though we estimated those probabilities very precisely, there's still risk on any single bet that we would make. Unfortunately, in simulation, both in simulation practice, in simulation software, and even in simulation research, we sort of focused obsessively on evaluating and controlling the error in estimating the mean, as opposed to thinking about the risk that's involved in making a decision. So I want to move towards a little more realistic example here than betting on highlight, but first I need to train you to look at a particular kind of graph. So let's start with a simpler example first. Okay, I call these eye chart examples because you know when you go to the eye doctor they say better, worse, better, worse. You're going to get to say better or worse here in a minute. And so imagine that we're interested in fulfilling orders and we want to make a promise to a customer or customers about how long it would take for us to fill their order. And it's a complicated system we have, or maybe we're implementing a new system, so we decide to simulate it. So the first thing we're going to do is simulate delivering 100 orders and see how long it takes us to fill those orders. Now I'm going to display the simulation results from the 100 orders in something you're very familiar with, which is a histogram. But over the top of the histogram, I'm going to put something that you haven't seen before, unless you're familiar with this particular kind of Moore plot. So there's the first histogram. And you can see that our order fill time ranged between about 5 days and 35 days. And the histogram shows sort of where the relative amounts were. But now I've added some things. That arrow pointing right down the middle, that's the average order fill time. That's the mean. The two arrows on each side, that's the 5th percentile and the 95th percentile, meaning that of those 100 orders we filled, 90 of them were between the arrows in the box, and 5 were outside on each side. And just to make it kind of clear, I've labeled those as likely for the things that are inside the box and unlikely for the things that are outside. Now, one more thing has been added to this plot, and it's very important. Along the bottom, those error bars you see, those are confidence intervals on how well we've estimated the mean, the 5th percentile, and the 95th percentile. We call this a Moore plot, a measure of risk and error plot, because it displays both risk in terms of the histogram and error in terms of those confidence intervals along the bottom. Now that was 100 runs. Let's up it to 1,000 orders that we deliver. Now is that better or worse? It's better, right? Certainly if you look at those confidence intervals along the bottom, in terms of how well I've estimated the mean and those percentiles, I've estimated them much better. So let's go from 1,000 to 10,000, better or worse? Right? Clearly better. This is not nearly as difficult as an eye exam. Right? Certainly better. But did the risk change? Right? Did the risk change as I added more of those replications? Well, no. Even though I've estimated, say, the mean very precisely, if we didn't want to disappoint our client, none of us in here would have promised the mean. We would have promised perhaps the 90th percentile if we wanted to be really sure to do it. So even though I've made my estimates better and better, I've run a better and better simulation experiment, I cannot simulate away risk. I can only estimate it better. Okay, again, just like the highlight example, I suspect nobody in here would have made this mistake. So let's up the odds one more time and look at an actual real example. So this is the magazine distributor's problem. This was an actual consulting project that I had a number of years ago. And so a magazine distributor distributes weekly publications to grocery stores and drug stores and department stores. And it's actually kind of a complicated single period inventory problem because it's not like the magazines all go in one place. Some of them go in the checkout counters, some of them go along the main line. There's some possibility of having to reshuffle or maybe being allowed to reshuffle the stock along the way. So you might have to, at least I had to, use computer simulation to find the optimal inventory policy. Now this is a situation where average matters. I would like the inventory restocking policy for these magazines to maximize my long-run average profit. I think that's a perfectly reasonable, absolutely sensible thing to do. Now one other little twist in this. You know, magazines have different levels of demand and they also behave quite differently, I learned. For example, some magazines, say like People magazine, hey, who's on the cover really matters. For The Economist, not so much, right? And so you get very different behavior of these magazines when you implement the optimal policy. So now you're really good at looking at more plots. So I'm going to show you the simulation results from looking at two magazines, one of each type, and I'll confess, I've tricked it so they both have the same long-run average profit. So the one on top, that's one like The Economist, where the cover doesn't really matter. The one on the bottom is one like People magazine, where if the right person's on the cover, you sell a lot. And if somebody's out of favor, maybe you don't sell quite so much. There's a lot more variability. And just to make it a little easier to look at, I'm going to put in a little dotted line at 0. Now, both of these magazines have the same long-run average profit. But imagine that that's all you told the client. And they start implementing this policy week after week and see very different behavior from the profits that they make. For the one on the bottom, I could have 3 out of 4 weeks where I lose money, right? Certainly possible, right? Whereas on the top, it's much more rare that I ever don't make money on a particular week. So even when the long-run average is what matters, if we don't convey any sense of the risk, then we've really failed in terms of displaying what the simulation results tell us. So the first reason that good simulations go bad is that we forget that we control error through the number of replications or the run length in order to measure risk. Because almost all real problems, risk is the thing that actually matters in the decision, even when the long-run average is what you're looking for. I have to, there we go. Well, thanks. Okay, number 2. I believe we are haunted by the ghost of Ronald Almer Fisher. Now, R.A. Fisher is actually one of my heroes, and it's easy to argue that he had the most profound effect on how we run statistical experiments of any statistician. Factorial design, fractional factorials, blocking, analysis of variance, hypothesis testing, all trace their roots back to the work of Fisher. And of course, any educated statistician, or engineering statistician for sure, today absolutely knows those methods and uses them. Now, among other things, Fisher looked at agricultural experiments. And of course, agricultural experiments, a growing season is a long time. Right? So data is very expensive. And so in developing experimental design, a la Fisher, classical experimental design is a structured approach to squeeze every bit of information that you can get out of very expensive data. And that's what it's supposed to do. Go ahead. All right. But you know, doing simulation is not at all like raising corn. I think we're dying. Individual replications are often very cheap, right, to get. Response variances can often differ substantially across what you're simulating. We simulate a lot of queuing systems in ORMS, right? And we know that in queuing systems, as you approach the capacity of the system, congestion increases explosively. If you simulate such systems, the output of those simulations, also the variance of that, increases explosively. So anything like an equal variance assumption doesn't make a whole lot of sense. Because the computer's doing the work, data can be collected sequentially instead of one shot, like a typical designed experiment. Apparently I have to stand over here. It's also the case that we may want to explore the design space somewhat interactively, because we have lots of factors that we can change in our supply chain or manufacturing, our risk simulation. We may want to explore those interactively as opposed to identifying all the factors that might affect things all at once. And finally, we can, and I believe we should, be driving our experiment by the error we can tolerate for the decision we have to make, as opposed to the amount of data that we can afford. Because oftentimes in simulation experiments, we can afford to do as much as we want. So we ought to decide what the error level we can tolerate to support the decision that the model is supposed to help us with. And asymptotic results make sense. Right? We can use results that are asymptotically valid because we often operate in exactly that regime. Now, it's certainly the case that people think about Fisher-like experimental design when they do simulations, but I think a lot of people have a sense that that's not exactly what they want to do when they sit down and do their simulation. Here's what I much more often see in practice. I see my slide not advancing. So you build the simulation model. You make some mistakes along the way, but you also learn something while you're debugging the code and getting it to work. You then choose an experimental design, which is maybe the default number of replications that the software specifies for you, or 30 because you mistakenly believe that somebody in a statistics class once told you that 30 is always enough. And then you try some sort of obvious scenarios that you thought might work, that thought you might be good designs or good ways to run the system, and they either confirm what you thought, or more often, after you see the simulation results, it gives you some ideas of other things that you want to explore. JJ, I think I'm just going to have you advance slides. Thanks. Now, there's absolutely nothing Fisher-like in that experimental design at all. On the other hand, an experimental design like that is going to leave you open to lots of errors because it's not a statistically sound design. So the issue is, can we have experimental designs that support the way that we actually want to do simulation? So we're going to do one more little simulation here. This is my mock-up of an interface for some simulation software. Thank goodness I'm not the person writing the interfaces. So let me tell you a little bit what you have here before we start the simulation. So this is going to be a production system design simulation. And you've got 5 work centers that I call A, B, C, D, and E. And what you're trying to do is decide how much capacity to put in each one. And what you want to do is minimize the long-run average cycle time for your products. And so you sat down and you had 4 ideas of how to allocate capacity based on what you knew about your budget or your intuition about things that you would do. Now what this is going to demonstrate is a statistical procedure that allows you to work interactively. So when we press go in just a second, it's going to go out and collect data sequentially on these 4 designs. And it's going to run until it can tell you with high statistical confidence which is the best of those 4. That is, which has the best expected value for cycle time for your products. But then you look at it and you say, oh, now that I've seen what works, I've got some other ideas I'd like to try. Now I've already typed them in, so they'll reveal themselves, and then it will try some more. And it'll try some more in a way that it doesn't have to go back and rerun the ones that it's already done, only the one that was still in contention. And then after you see those, oh, now I've got a couple other ideas, let me try those as well. And at the end, we'll still have an overall statistical guarantee that we have selected the best system, even though we did this in an entirely interactive way. JJ, let's go. Okay, so when we press the go button here, it's going to go out and collect 10 replications on each of these alternatives, and then it's going to start sequentially adding replications to them until it can eliminate and only have one that's the best. And there's a statistical confidence guarantee that you actually have selected the best one. Right? That's what these kind of procedures do. Okay, so you can see it got rid of the 4th one very quickly. There are 3 that are still in contention, but now the first one's dropped out. Active means it's still in contention. And now at 23 replications, it said the 3rd one is statistically the best. But we looked at those 4 and said, oh, you know, I can see some others I might want to try, having seen what worked well, and so now we're going to add in 3 new ones. Okay, I admit I'm not an interface guy. But we're going to add in 3 new ones, or 4 new ones, and now they start running. And the procedure, if anything, only has to simulate the one that was left over from the first round, still provides the overall statistical guarantee that you found the best. I set this up so it wasn't going to take long, and very quickly now, oh look, we found an even better one. And finally, we'll end up with 3 more, which now looks like a little bit of a waste of your time as long as it's taking, but it won't take long. Now this is sort of an interactive optimization, person in the loop, right? No algorithm is doing it. You're making the decisions about what you want to try, but you still want to have statistical confidence at the end. To me, this is much more in line with what people want to do with simulations than a Fisher-like design. Okay, so it turns out the last one you tried was actually the best. Congratulations, you're an optimizer. All right, let's go ahead. So the second reason that good simulations go bad is that we either use no experimental design at all, or we use an old experimental design that constrains us from what it is that we really want to do. Okay, simulation optimization. So we did interactive optimization. Now let's talk about using an algorithm to do it. So since mankind first built simulation out of rocks, sticks, and cow dung, there's been a desire to treat the simulation as the objective function in an optimization, right? You write a simulation, you got things you can change, you just naturally want to treat it as the objective function. Some examples of things that you might do: how many and which redundant components should I put in a highly reliable system to maximize long-run availability, subject to a budget constraint? Here's one we particularly like to do in Chicago: set the red, green, and left turn arrow cycles to minimize the aggregate driver delay along Lakeshore Drive, for example. Or decide how many of each product variant to stock to maximize the expected value of profit. Right? These are examples of simulation optimization problems. We have an objective, say an expected value or a long-run average sort of objective, and we've got things that we can change. Now, simulation optimization is hard. First of all, the objective function is implicit in the simulation code. And often we have no known properties, anything like convexity, right, out the window. We don't have any idea. And of course, you evaluate the objective function with noise. This talk is about stochastic simulation, so the best that I can do is estimate the value of the objective function. I might have a mix of integer, categorical, and continuous decision variables, with integer ordered decision variables being most of what I see in OR applications. And the evaluation of the objective function may take from seconds to hours to run that simulation. So it's not instantaneous like putting it into a linear objective function. So what do people do to solve large-scale simulation optimization problems? Well, the software world is dominated by meta-heuristics, and the research world has mostly focused on ranking and selection, adaptive random search, and steepest descent algorithms using gradient estimates. What I'm about to say next applies to all of these. So it doesn't matter which of these methods that you're using, the way that good simulations can go bad here applies to all of them. Oops, one too far. Can we go back one? There we go. All right, so this is our last little demo. We've got a simulation optimization problem with only 10 feasible solutions, right? Trivially small problem. I've numbered them 1 through 10. The true expected value, think of it as cost, those are the blue diamonds. So lower cost is better. So the 8th option, that's the optimal solution. But of course, you don't know this, right? You have to run the simulations, but today in this lecture, you get to know the answers before we actually run it. Now we're going to run the simplest possible globally convergent simulation optimization algorithm. And here's how it's going to work. On each iteration of the algorithm, the current sample best solution, the one with the best sample mean, will get a few more replications. And one other of the 10 solutions will be randomly sampled, and it'll get a few replications. Next iteration, whichever one has the smallest sample mean, gets a few more. We randomly sample one of the other 10, give it a few more as well. The reason it converges is because eventually you simulate them all infinitely often, right? So convergence is pretty easy. The x's along the bottom are going to be the sample means. So when the x sits along the bottom, that means we haven't simulated that one yet. And when it pops up, that means we've taken some replications and that's the current average. Now what I want you to watch as it goes through several iterations is, on each iteration, which one is the current sample best, right? That's the one with the lowest x. And what's the direction of the error that we're making? Okay, so let's run. I use this little demo to talk about lots of different kinds of things, but this is going to be a global search. And each time I click it, it's going to do it. So we're going to have the first iteration here in a second. So solutions 3 and 10 got sampled. We took 2 replications of each and averaged those. Right, so solution 3 was the best. On each iteration, the one with the lowest x is the current sample best. It gets a few more replications, and one other gets a few more as well. Right. Oh, finally we sampled solution 8, but it turned out its objective was a little high. Now it turns out solution 8 looks good. By the way, we haven't ever looked at 1, 6, and 9 yet. Oh, now suddenly 9 we looked at, and even though solution 8 was the optimal solution, for an iteration there we didn't recognize that. And we're only going to go along for a couple of iterations. More iterations, right? So I stopped where we would have actually made the right decision, right? But of course, in a real simulation optimization problem, stochastic optimization, you have no idea when to stop. And all along the way, various solutions were vying for the best, and think about the direction that they were off from their actual values. Let's go to the next slide. So what kind of errors can you make when you do a stochastic simulation optimization? Well, it always works when we both press together. Well, the first error you can make is you don't find the optimal solution. Well, we never sampled solution number 1 there. Had that actually been the optimal solution and we had stopped, we would never have seen it. There's not a whole lot you can do about that, right? If you don't look at every solution and you have no properties in the objective function, there's really no guarantee. Okay. But this is what troubles me more. When you do stop, you don't necessarily recognize the best solution that you actually did simulate. Right? There were many times after we had simulated solution 8 that some other solution's sample mean was better. Okay? And finally, when you do stop and you pick one of those solutions, you're likely to have a misleading idea about how good it actually is. Because the bias is always in the favorable direction. Right? If it has a sample mean that's too small relative to its true mean, that's when you pick it. Right? So the bias makes you think that when you implement it, it's actually going to perform better than it really does. So what's the solution? Is there anything we can do about that? Well, I have no answer for the first bullet. That's what my friends in the research community are always working on. But I do have an answer for the second two. Once the optimization is done, we don't have to be done. We can do a little statistical cleanup after the optimization. Think of the optimization as the first stage in an experiment. And now we want to add just enough additional effort, just enough additional replications to guarantee that the solution we pick is the best or near best of all the ones we actually saw, and that we've estimated its value to within plus or minus whatever matters to us to support our decision. This is easily doable with simple statistical techniques. So the third reason that good simulations can go bad is that we settle for what the optimizer gives us without doing a little effort to clean it up and be sure at least that we're picking the best of the ones that we're actually simulating. Okay, last topic. Everything I told you is wrong. All right, that's a hard confession for somebody who's taught simulation for 30 years to make. But let me illustrate what I mean through a simple example. So I'm going to let y be the steady state expected number, steady state number of customers in an infinity queue. That's a queue with a plus on arrival process, exponential service times, infinite number of servers. Think of it as a self-service system. Now the true arrival rate is lambda c. The true mean service time is tau c. Those are out there in nature and I don't know what they are. If I knew what they were, I could get the expected number of customers in the system as lambda times tau. Well-known result. No reason to simulate this system at all, except that I want to illustrate a point. So for a moment, wipe your minds clear. Suppose you didn't know that mathematical result, and you said, I'm going to figure this out by simulating. All right, so our little thought experiment is, how would I get this by simulating? All right, so here's my stylized simulation, which I regret to say is not that much different from what I teach people in class. So I'm going to take part of the hard part out. We know the arrival process is Poisson. We know the service time is exponential. I just don't know the parameters. So I go to the real world and I observe data. A1, A2 through AM are inter-arrival times of customers. And I estimate the arrival rate, lambda sub c, the true arrival rate, by 1 over the mean time between arrivals. That's a possible estimator I could use. Similarly, I estimate I go out and observe some service times. There's no reason I'd have to observe the same number, but I'm trying to make it simple so we can see a result. S1 through SM, and I estimate the true mean service time, tau c, by S bar, the average of the service times. Okay, so I parameterize my model with real-world data. I now run n replications of the simulation. Now, just to make the math easier for me, on each replication I just take one observation of the system in steady state. In reality, you take an average over a period of time, but so I can show you something on the next slide. Each of those replications I take one observation. And then I do completely the natural thing. I average those observations of number of customers in the system, and I use Y bar to estimate the steady state mean number of customers in the system. Now, on the next slide, I want you to remember two things. M, that was the amount of real-world data that I had to parameterize the model. And N, which is the number of simulation replications I took to estimate the result. So this example is so simple, I can compute everything I want to about Y bar. For example, what's its expected value? Gee, I'd like for it to be lambda c times tau c, because that's the real answer, but there's bias. And that bias depends upon how much real-world data I have. That was M. What I'm more interested in today is the variance, because the variance says how much error is there in my estimate. And you can see it has two terms. The term that people like me talk about in simulation classes all the time is the blue one. That's the variability based on the amount of simulation effort that I did. But if I integrate across both types of error, the fact that I ran the simulation and the fact that I had to estimate the parameters from the real world, there's a second piece of that error called input, which I call input uncertainty, which may completely overwhelm the first part. Right? And this is what I mean about how everything I told you could be wrong. If I'm judging how well I've simulated solely based on the simulation variability, I could be missing an overwhelming amount of other variability that should affect my decision. So what can we do? Is there anything we can do to get a hold of that red term? Hey, this is a simulation talk, so more simulation must be the answer. So let's think about what it was that we did. There's the real world, which I represented as a cloud, and it has some unknown distribution I call F. Right? We model it as having a distribution. Let's talk about the inter-arrival times. I went out and got a sample of real-world data, and from that real-world data, I fit my input model. Now, the red term comes around because, let's do the little thought experiment here, I could have gotten a different sample. Right? If I went back to the real world and I got M more observations with the superscript 1, that would have given me a different distribution. Or if I had gone and done it again, I would have gotten a different distribution for inter-arrival times. And that red term reflects that input uncertainty. That's what input uncertainty is. That you could have gotten different results had you gotten a different sample of data. Well, this is, of course, a really expensive way to solve the problem, which is to go out and get more data repeatedly. But in fact, there's a simulation way out of this. So I'm going to create empirical world. I'll take the data that I actually observed and pretend like that's the real world. I can resample that data the way I did in my thought experiment where I resampled the real world. Now I'll resample empirical world, and I can run simulation experiments at the different input models that I would have gotten. And that will be a way to represent how much uncertainty there is in my results based on the uncertainty there is in my estimate of the input models. Okay, and this is called bootstrapping in the statistics literature, but the basic idea is clear. We let the empirical data stand in for the real world, which we can't resample. So the fourth way in which good simulations can go bad is that we ignore a big risk, which is input uncertainty. So recently, the renowned statistician Brad Efron published a book on large-scale statistical inference. Really, really good book. And in that book, he gave what he called sort of a simplified history and future of statistics. So he thought of statistics as starting with the age of Quetelet, which was he was the first person to really apply large-scale census data to answer important societal questions like, is the rate of insanity increasing in our population? Then we moved into the classical period, which we're all familiar with. Pearson, Fisher, Neyman, those folks. And their focus was optimal inference, squeezing the last little bit of information that you can get out of really expensive scientific data. Still to answer relatively simple questions like, is treatment A better than treatment B? What Efron argues we're in now is the era of scientific mass production, where teams of scientists in a lab can produce vast amounts of data, where they want to look at thousands of hypotheses or estimates simultaneously. And Efron argues that we need to think differently about statistics in the era of scientific mass production. So to close, I'd like to give you Nelson's simplified history and future of simulation statistics. So for me, the big advent of making simulation statistics easier for users in general was when the software anticipated what you might want. So you build a model in the simulation language, and if you got a queue, it's going to compute mean waiting time. If you got something modeled as a resource, you're automatically going to get utilization. That made it very easy to both build models and to get statistical performance measures out without having to do a lot of extra work. Certainly today, every simulation language and every well-taught simulation course treats simulation as a statistical experiment. Right? The languages allow you to set up and manage multiple scenarios. They make it easy for you to control the number of replications or the run length, and they give you confidence intervals on the things that you estimate, recognizing that in fact it is a statistical experiment with statistical error. This is where I think we need to move. Experiment design and analysis driven by the decisions that they are to support. I want not only measures of error, but measures of risk, including input uncertainty, to be the default display. We should have experimental designs not that asks us for something abstract like the number of replications, but asks us for how much error we can tolerate or how much time we have and does the best that it can given those inputs. I also want experimental designs that support the way we want to do simulations, so that if we want to interactively work with the model, as opposed to turning it over to an algorithm or doing a design experiment, the experimental design should support doing that correctly, because that's what we often want to do. And finally, simulation optimization algorithms that both have convergence guarantees, which I think is extremely important, but also have statistical cleanup at the end to make sure that we really get correct inference out of what we've done. And that's all I've had. Thank you very much.